This video is going to talk about related rates, which is one of the dreaded sections on word problems in calculus. And it's going to really rely on knowing some geometry formulas and then using your derivative rules on them. So let's read the first question here. It says the radius of a sphere is increasing at a rate of 2 feet per minute. How fast is the volume of a sphere increasing when the radius is 5 feet? So we're talking about a sphere here, and we're talking about a volume, so you need to know that the volume of a sphere is 4/3 pi r cubed. That is our formula. Without that, we literally would not be able to solve this question. Now that we have that, let's see what they give us in the problem. They give us that the radius is increasing at a rate of 2 feet per minute. So that does not mean that the radius is 2. That means it is increasing, or its rate of change is 2. And so that means the derivative of r with respect to time is 2. Okay, so that's our dr dt. And then they also tell us later that r is 5. And then what is the thing that we are trying to find in this problem? We are trying to find how fast the volume is changing. So that means we want to find dv dt. Okay, so if we know that v is 4/3 pi r cubed, well, then I can take derivatives of both sides, and I can say dv dt is 4/3 pi. It's constant, so it just comes along for the ride. And then the derivative of r cubed is 3r squared, and then by chain rule, dr dt. Now once we have that, then I can plug in the things that we know. We know that my r value here, my r value is 5, and my dr dt is 2. And so then if we multiply that all out here, we're going to get 200 pi, and the units for the volume is going to be feet cubed per minute. So again, this really comes down to what is going to be the geometry formula or some other related formula that is going to tell us how things are related in this problem. And then secondly, what values do we have? What values are we looking for? And then on top of that, take the derivative of your formula to work things out. Okay, so this next one here, it says that we have a 10-foot ladder resting against a wall. So I'll try to draw a little picture here. So we got this ladder here, and we know the ladder is 10 feet long. And now that we know it's 10 feet long, we know that it is being pulled away from the edge, and it's being pulled away at a rate of 2 feet per second. And we want to find the rate that the angle between the ladder and the ground is changing when the base of the ladder is 6 feet away from the wall. Okay, so that's what we're trying to find here. Well, we need to find some sort of a way that can relate the angle and this distance here, which I'll call, say, x. We need to find some way to relate that. Well, it looks like I can use sine. Sine of theta would be, sorry, not sine. We'll use cosine. Cosine theta would be x over the hypotenuse of 10. And so then we could take derivatives of both sides and get negative sine theta d theta dt is equal to 1/10 dx dt. And so now we plug in the things we know. We know that dx dt is 2. That's how fast it's increasing. That's how fast this side here is increasing by. The problem is I don't know what sine theta is, but we can actually figure it out here. If we know that this side is 6, then by Pythagorean we can see that that side is going to be 8. If that side is 8, then sine of that angle right at that time would be 8/10, or 4/5. And so then we would have negative 4/5 d theta dt is 2/10 is going to be 1/5. And this would then be d theta dt is negative 1/4. And this is how we get our answer here. So again, I do kind of want to point out that this process, I mean, it's not really sufficient to see 2 examples here. There are lots and lots of variations that we could possibly have. However, this does show you the general idea of these, and you just have to adapt it using a different formula for each problem.